our first speaker, Larry D. Olson with Olson Engineering. And you'll see there's two locations there, Wheat Ridge, Colorado, as well as Rockville, Maryland. Larry mentioned to me he just recently relocated back to Colorado. And he's going to be talking, as you can see in the title here, in terms of emerging NDE methods for evaluating monitoring bridges, two specific subtopics, impact echo and surface wave scanning of bridge decks. And secondly, imaging by Interferometric survey for bridge monitoring and stable K forces. And with that, help me welcome Larry Olson.
Thank you very much, Professor Myers, John, for that introduction. We'll get right to it and go through this here, even though we have a little more time because of the unfortunate cancellation of one of the talks for sure. So basically, you already know the general topic. You might say, what the heck is imaging by interferometric survey? Did any of you know that that was actually interferometric phase radar? That's what it means. We'll talk about that. It's like, you may have heard about INSAR from space, looking down on the Earth. This is terrestrial, and so we'll talk about this technology. Okay? So we came up with the impact echo scanning. First did it years ago. I had a U.S. patent. It's expired, but for looking at voided versus grouted ducts in post-tension bridges. It's a scanning technology rolling along structural concrete where you'd impact every inch and get an impact echo result. Well, we got some research a while back to adapt the idea to bridge decks. Now, obviously, they're much rougher than structural concrete, so we had to do some differences in how we made the technology work. But we were using impact echo, which has an ASTM standard. I'm also a member of 228, the Nondestructive Testing Committee, and the method is discussed there in the document, as well as surface waves, spectral analysis surface waves. Developed years ago when I was in graduate school, started it by my professor at the University of Texas at Austin, Ken Stokey, and then Sohail Nazarian came along and did a lot with the technique, as well as many of his other students. Started off being largely for geotechnical applications, but it's been used a lot on pavements and structures as well now, as multi-channel analysis surface waves related to it is more typically used for a geophysical site nowadays to get seismic velocities. So I suspect most of you have heard of the impact echo test, developed originally by Nick Carino and Mary Sansaloni. It's a resonance test. You impact the concrete surface. You look for the resonant echo. That's why it's called echo, but it's really a resonance test. From the backside of, say, a solid concrete slab or a flaw, like void, cracking, honeycomb, things like that. And so you get a signal in the time domain. The echoes are there, but they're not so apparent. By using the fast Fourier transform technique, you can get a resonance. And if it's a 1 foot thick concrete, this would typically be resonating with an echo. If it's a slab, a single resonance of about 6,000 hertz. So the depth in a simple sense is equal to the factored impact echo compression wave or sound wave velocity divided by twice the frequency of the resonance. So what does that really mean? Well, 1/6,000th of a second, 6,000 hertz, means the echo time inversely related is 1/6,000th of a second. So if you had an echo at 12,000 hertz, that would say you had a crack at 6 inches, as opposed to seeing all the way through it. So having said that, I thought this slide might be useful to show, and it does also apply to columns and beams and such. However, they have multiple resonances, not as simple as the flat slab resonance of a plate-like shape, whether that's a tunnel lining, a pavement, or a deck. So in a normal situation, sound concrete of a deck, you get one primary resonance, back and forth, as it resonates. By impacting the surface and picking it up, typically it's either a displacement type transducer or an accelerometer, and then you end up displaying it as the linear spectrum of the displacement spectrum. So what if you have a crack that's partial or a tight crack? You can get two resonances, two echoes. One is the full thickness echo, and then which is at this same frequency, but then you see another resonant echo here that would correspond to a shallower depth at a higher frequency. So as you go deeper, and if it's a more severe crack, you really may see some distortion of the lower frequency if you see a backside resonance at all, but you see an echo that's strong in this case from a more complete crack, maybe limited contact. Any crack that is completely open, like a typical delamination, you won't see deeper because that sound wave is totally reflected at the concrete to air interface. So to the extent there's some contact across the crack, you might see 2 echoes. Of course, at the lamination, in the final one, you can see that echo, but not without using really high frequency sources and impacts to get the depth. So most of the time, what you actually record and analyze is the fact that it is so audibly apparent. Anybody that's ever done any chain dragging probably knows you hear a hollow drummy sound. That's the flexural resonance. No longer an echo resonance, but it's the flexural resonance of that severe delamination of the top steel if you're testing on top of a deck. So that shows up as a very high amplitude and a very ringy signal in the time domain. And so normally, if you wanted to see that echo, you'd have to have a source that took you very high in frequency to see, oh, that's 2 to 3 inches deep. So normally you identify it based on the flexural resonance, which is that audible sound we all hear from a true delamination in the top of a deck. So having said that, I thought I'd mention briefly surface waves, and I'll talk about it more in a minute. On concrete, we're often using it. This is a device where you'd hit with a small hammer nearby and measure the velocity of a surface wave between 2 receivers across, say, a vertical crack in this case. You can actually get the depth of that crack by looking at when the velocity starts to increase beyond the wavelength in the tip. You can use it for fire damage, for alkali silica reaction, general concrete quality evaluation, because both impact echo and surface waves can be done from one side. It's not like ultrasound where you have to have access to both sides to do the test generally. So by having 2 receivers and testing across it with an impact source, you generate surface waves. And proportionally, a surface wave is about 56%, 0.56, the velocity of the speed of sound in concrete. That's just the physics of it for a typical Poisson's ratio around 0.2 for concrete. All these elastic waves, shear waves, Rayleigh waves, so-called surface waves, and compressional waves, sound waves, are all related by the elastic constants. How many of you remember freshman physics? Anybody? It was back then. You looked at it. So, because it's difficult to evaluate large structures point by point, we wanted to be able to do some scanning. Because point-by-point testing is tedious, takes you forever, it's not so fast. Now, this is not fast, but you get a lot more data than you can doing it point by point. So here it's being shown rolling it on an asphalt overlay deck. I'll talk about the unique reason surface waves can test through asphalt overlays in a minute. But you've got basically the system, ruggedized computer, the signal conditioning, the rolling wheels, I'll show a picture of those in a minute, with impactors every 6 inches. I will mention that this is both the Iowa DOT and now the Indiana DOT have purchased a system as Olson Instruments from us because, and Indiana in particular has done a lot of decks, like 100 decks, because they want a very detailed project level damage map of whether to repair, replace, or maintain a deck. So that's what they're using it for. And bare concrete impact echo mode alone, it's harder to do the surface waves, as you'll see in a minute, for asphalt overlay. So the basic wheels look like this. They're heavy. The sensors protrude out a bit. It's a displacement transducer with a urethane tire over it to protect the transducer. But that puts this fairly heavy wheel couples to the rough concrete. So as we're rolling it, we then impact it with a solenoid. So every 6 inches it's timed so that as this rolls to the bottom, it applies an impact to the concrete. Hits it fairly sharply. Now obviously, if you test on air with either the sensor or the impact, you won't get good data. But you're getting data every 6 inches. So it's a lot of data. So to miss an occasional point when you don't get good results is not so bad. But it's intentionally designed to deal with the very rough surface of a typical concrete deck. So having said that, this is a typical scan. This is 0 to 100 feet. It was a 300 millimeter or 12-inch thick approach slab. This is 100 feet long. That's 200 tests. And it came in good. It was there was really no delaminations. It was a brand new deck. They were worried there might have been some void issues because the concrete set too fast on this particular project. Well, it turned out okay, although they had surface, long-term, short-term drying shrinkage cracks, drying plastic shrinkage cracks that happened too quickly. They had to coat it, but there was not a problem with consolidation of the deck. The signal from this location looks like this in the time domain, but you can see in the frequency domain, the linear displacement spectra from 0 to about 50,000 hertz, that this is showing a very distinct echo that corresponds to that nominal 8-inch thick deck. So if you calibrate based on a known deck thickness, you can get a very accurate within 2% deck thickness out of the impact echo test. So this is a research study that we participated in. Rutgers University had the SHARP 2 grant called R06A. You can find their report online. And they were tasked with looking at all the different non-destructive evaluation methods for evaluating decks, trying to improve beyond chain dragging. So they looked at a whole range of technologies. They invited people to participate. We volunteered, as did others, to demonstrate technology on the project. So this just shows they chose a very focused area of this deck to examine. It was an older deck in Northern Virginia. And they did both traditional, they did some coring after the fact. They did chain dragging. So interestingly enough, this is the impact echo result for the top steel of scanning with the wheels spaced a foot apart, testing every 6 inches over this test section. And this was such a good specimen, interestingly enough, when they tore the bridge out a few years later, the Turner Fairbanks Highway Research Center in McLean, Virginia, Langley, Virginia, wanted the deck section. So they moved it over to their laboratory as a full-scale specimen instead of just demolishing it. So they liked this because it had real-world delaminations. So it has been preserved, which is interesting, as there is a new bridge there now. So what we found in the yellow to the red, we identified the various areas that were indicated by impact echo to be top steel delamination. Well, they did acoustic sounding. The Rutgers students did it. You can see in comparison that there's more detail in the impact echo, not surprisingly, than there is in the sounding. The other interesting thing is that right here, the students did not hear the delamination that was predicted by impact echo. And that when they cored it, that delamination was found to be at 3.5 inches deep. This one they did hear, identified by impact echo as well, that it was 2.5 inches deep. So basically, I've kind of concluded from years of experience that you can't hear much deeper than around 3 inches. It's going to be problematic. So that was an interesting practical finding of the whole study. So the other thing that's useful is if you don't have a top steel delamination, you can see to the bottom. So you can see in the lighter color here, the light blue, that there are some areas of bottom delamination. This is also of interest to DOTs. Now, where you have a top delamination, you're not going to see through that to the bottom. But other areas, you can see that with impact echo. So, and then you estimate areas. We also did some comparison radar with a system called Aladdin by IBIS-S GeoRadar. This just has 2 antennas. You can go front to back, side to side, or even at angles. And out of that system, this is the radar results. And you see right here, when you use ground penetrating radar, we and others have used it, it's really more of a damage potential technique. In other words, you can find areas that are likely corroding and potentially delaminated, but the problem is you're depending on the attenuation of the signal because the rust byproducts, the de-icing salts, other things that are down there in a delamination zone cause an attenuation of the signal. And because of that, it's not necessarily damage, it just indicates likely area of damage. But this was calibrated to pick the thresholds of attenuation based on the impact echo results. And when it's done that way with calibration, however you choose to do it, you can get fairly good results showing, and you can see the correlation was fairly good between the radar and the impact echo scanning. But this is a damage map. This is a potential for damage map, is how you should think of radar. Of course, it's very useful for getting depth of steel, estimating remaining service life, the concrete cover, all those other good applications. The bottom, again, shows for comparison's sake the acoustic sounding, chain dragging type results by Rutgers. So, fortunately, most of our decks are not asphalt overlaid, but certainly a number of decks are. And so the Colorado DOT came to us and said, and we talked to them about it, and we did some initial testing to demonstrate, based on some research we'd done, on another SHARP 2 project, which we participated in. The National Center for Asphalt Technology at Auburn University got a grant to look at delamination of asphalt pavement layer lifts. In other words, debonding as they place new asphalt. That can be a problem if the TAC code is not properly applied. Well, that debonding is much like an delamination in concrete because it's a horizontal plane. So from that, we had learned that surface waves could actually detect at 2 inches and 5 inches. Initial blind study, meaning we didn't know what was there. We did the evaluation with surface waves and impact echo. And impact echo was useful when the asphalt was colder, But as soon as asphalt warms up, impact echo does not resonate well. So consequently, we were able to find these debonding, and we said, well, maybe we can look through an asphalt overlay deck and tell if it's debonded asphalt based on radar and knowing the depth of the asphalt, or the top steel or the bottom steel, because of this more severe problem being a delamination, a real lack of contact at the plane of true delamination. So that's what we did. It's an early version before we had built a cart of just pulling the system along with the wheels. You'll notice that instead of being offset 3 inches, so you get impact echo test left and right, they're pulled closer together instead of being a foot apart, and they are lined up. So you get one impact echo test result on this side and a surface wave test between them as we pull it. And that's 6 inches apart. If it's really thick asphalt, we might go to 9 inches apart to do the testing. So in doing that, this is an example. You get 2 time domain signals. This is time and voltage, the close wheel, the far wheel. The impact was next to the close wheel. And the peak energy is actually the surface wave, because about 67% of your energy of an impact goes into surface wave. Only 7% is compressional impact echo type waves, and 26% is shear energy. That's just the physics of impacting a surface. So the surface waves, you want to window in on them, and that's what you actually do. You focus on this big peak, and you get something called phase, which goes from 0 to minus 180, jumps to 180, comes back down to 360. When you're 360 degrees out of phase from the far receiver to the second, from the close receiver to the second, that means you have one wavelength, or it's 6 inches. So back to freshman physics, velocity equals frequency times wavelength. So that's the basics of the test that Professor Stokey and his students developed. So what you've got then is this is nominally right around 10,000 hertz here, times a half foot, that's about 5,000 feet per second. This is a plot showing it's around 5,000 feet per second from wavelengths of 1/10 of a foot, approaching longer here, up to a foot. So in any case, this is showing sound asphalt on similar concrete. It was relatively cool in Denver when we did this testing, so the asphalt wasn't much different in modulus and velocity than the concrete. So this shows an example of asphalt debonding. Now, instead of having a regular phase curve, this delay here corresponds to a drop in velocity from nominally 5,500 to 4,500 feet per second. That occurred at the depth of the asphalt because it's a lack of contact. So it's like a soft boundary, if you want to think of it that way. There's contact. Energy goes across it, but it's not stiff because it's no longer bonded. So that drops the velocity, and that shows up as this phase delay and this drop in velocity. So this is an example, and I should have pointed out one more thing. This is wavelength, which is approximately depth from 0 to a foot. So right in here at about 0.33 feet or so, it's 3.5 inches right here. Now this would be 4/10 of a foot, 6/10, and so on. So on this plot, now you see again a delay in phase, but it's at a longer wavelength, a greater depth, and that shifts it to the right. That drop in velocity happens at 5.1 inches. So if you're doing radar or otherwise know the asphalt thickness, this is into the concrete. This is the top steel delamination. It was bonded asphalt, but now it's showing up at the depth of the top steel, this drop in velocity. This is an interesting result because 2 things happen. At 3.2 inches, there was a drop in velocity corresponding to the asphalt debonding, but it's still in contact. Gravity still has these in contact. It's just a weak interface, is the way to think of it. And then at 7.4 inches, it drops again. That's at the bottom steel depth. So we were seeing both the debonded asphalt and a bottom steel lamination. So we did a couple decks. We've since done a number of decks with asphalt overlays. But what they did, it was an initial blind study, meaning the DOT said, okay, give us your report, then we'll take photographs of what we find when we scrape off the asphalt and use hydrodemolition to remove the loose concrete where it is delaminated, get it ready for repairs, because this was a real world project. So that's what they did, and that's what we did. On the left is the plot in the colors from 50 to 70 feet, 4 to 8 feet in, of where we predicted through the asphalt overlay deck before removal of the asphalt where it was delaminated. We had an excellent correlation. This is scaled a bit, 60 to 70 feet, 4 to 8 feet. But you can see as outlined where the concrete was loose and broken up and spalled because of the corrosion of the steel expanding typically up to 6 times in volume, causing this tensile cracking called a lamination. But nonetheless, you can see very good correlation between what we predicted and what they found. So we've gone on to do a number of decks with good success. We're not finding tight cracks. I don't want to overemphasize it, but we are finding delaminations, which is what they're after on the decks. So just some quick summary comments about that. It is slow walking because you don't want it bouncing a lot. So you're going about a mile an hour, just a slow walk across there and doing just typically impact echo if it's bare concrete. It finds top delaminations, even the bottom delaminations can be found where no top delaminations are present. The combined impact echo and surface waves technique can detect top and bottom delaminations in asphalt overlay decks and for debonding of asphalt pavement lifts. The most accurate damage mapping of bridge decks is done by this combined approach. And that was shown in the Rutgers study and other studies, because impact echo is a very good technique. The stress waves interact quite well with cracks, with more so than radar. Radar is a damage potential. We like radar, don't get me wrong, but we do both. And it's a better damage map where radar is more of a damage potential. So I guess since we have a little time and this topic is over, did anybody want to ask a question right now before I go on to the next topic? John, Professor Byers.
I'll ask a question. So the magnitude of the drop in the velocity.
Yes.
You might want to repeat this question because I'm not at the mic.
He's asked, okay, go ahead.
But does that tell you the level of the delamination, the magnitude of the drop, or just that there is a defect?
Because it's just data, I don't think we can necessarily grade it between a tight crack and delamination. It tends to, if it's a tight crack, you won't see much velocity drop. You might see an echo, but it's generally more of an aerial thing than it is in delamination. But good question. Okay. Any other questions before I continue? Yes, sir.
So the combined impact echo and surface waves,
Mm-hmm.
you did with asphalt overlays.
Yes.
Have you ever done any work with concrete overlays? And what's the difference between T-bond, the surface, and the top bar crack and the base concrete?
Yes, we have done some white topping surveys. And often impact echo alone, depending on the thickness of the white topping, will work. But if it's too shallow, because you'll still look at the impact echo, but you can run it in surface wave mode to check as well. Yeah. Okay. Any other questions? Yes, sir.
Do you think it's possible to detect bond from the distress strands?
Specifically, if it's a plane, like a delamination, yes. If it's isolated and very small, you'd have to check it and see if you could do it. We also have a handheld scanner for impact echo in that case to see if you would see anything that's designed for smooth structural concrete. But it tests every inch as opposed to every 6 inches. So some of this in nondestructive evaluation, as you can appreciate, when you have a new application, the proper procedure is to evaluate whether you think you have a chance of success based on knowing all the geometry, and then do some initial testing and do ground truthing destructively to confirm were you successful or not before proceeding into a larger project. So the next one is a system that's manufactured by IBIS-S GeoRadar. They're an Italian company that's now owned by a very big company called Hexagon that also owns Leica, but I might have a timer on this. If I do, that's too bad. In any case, it has applications on the left for landslide and dam monitoring, where it steps along a 2-meter long track, and you can very precisely see movements of landslides out to 2.5 miles and big structures like dams. Are they moving? It's one-dimensional. It's speed of light radar. The system on the right is the structural system. We've used this on both buildings and bridges, primarily bridges, but it sends and receives from these 2 air horn antennas the radar signal, which is very high-frequency radar. So it's continuously sampled. Basically, there's another view with a bridge in the background. Interferometric phase radar means you've sent a signal out, and this is 17.1 to 17.3 megahertz radar, meaning it's nominally a 3/4 inch wavelength, where most structural radar is between, say, 1.5 to 3 gigahertz. So it's an even higher frequency than structural radar. But as you are there, under a bridge, it's trigonometry. You have some angle limitations. You'd ideally like it to be 5 to 1 to get a good reflection, because it's straight at a reflector. You turn that into a vertical component or a horizontal component if it's a building. You can go as flat as 10-to-1, but you lose some accuracy. Speaking of accuracy, I might not have emphasized this. Because it's line of sight, speed of light technology, it is amazingly accurate. You probably won't believe it, but they've proven it in the research and the theory. You can resolve the movements of a bridge to 4/10,000ths of an inch. Think about that for a minute. It is extremely precise. On a landslide, it's 4/1000ths of an inch. On a bridge, you can see up to about 100 hertz in resonant frequencies. So it's a really good technology that has some significant advantages. It's basically for medium to larger bridges, medium span to larger bridges. So by resolving the vertical component, you would see it move. This is an example on a post-tension segmental bridge in Colorado of showing the reflectors are mounted up here. You kind of see them sticking out because on concrete, if it's a steel bridge, it'll reflect from steel elements often. But on concrete, you will usually need, you always have to add a reflector to reflect the radar waves. So set it up on the ground. These are the reflectors. They look like this. They're triangular. You point them approximately back at your unit, mount them on the top or the bottom. You can mount them different places. And then when you shine the radar into the sky, they stand out as powerful reflectors. So it's a bit of a distance finding mechanism as to where they're located, as well as seeing the reflection and the movement that they are recording as they move with the bridge. So it was a windy day, and it actually, the oscillations, this is not much movement. The peak movement was 2.26 millimeters, which is not very much, nominally 1/10 of an inch, from a 40,000-pound truck. And it wasn't a big truck. But the wind was moving it, making it oscillate. And so at these 5 different corner reflectors, you saw these results as the truck drove by. Out of that, we also measured the natural frequencies. And this is from like 0 to 12 hertz nominally. But the natural frequencies are listed from 1.3 to about 4 hertz as peaks at these different locations. So you can also use it for modal vibration testing, as well as displacement monitoring of the bridge. So this bridge had a larger truck on it. It was part of the FHWA's long-term performance program, monitoring a New Jersey bridge with the IBIS-S. Drexel University was also involved and used string potentiometers. So we ended up with a comparison. Because it was steel with a steel deck, we thought the steel pan deck would reflect too much. We did mount reflectors. With that steel pan deck, we'd just see too many signals coming back. Had there just been the beams and the cross frames, we might have gotten away without mounting the reflectors. But if you see too much steel, it's always reflecting. So we mounted them up there, set up the unit, and you can see from nominally 0 to about 0.8 of an inch with different positions, with load tests stopped, they brought out trucks at 3/4, 1/2, and quarter span distances with 6 trucks were moved out each time. And these are the corner reflector displacements over about an hour. So this was in essence a load test to see how the bridge deflected as part of their studies. And so had very good accuracy, excellent correlation with the string displacement potentiometers that Drexel used to the ground, and we didn't have to touch it. So it just showed the displacements quite well. So I'm going to touch on one more thing where it's very useful. We've done some resonance testing of cables, traditionally with accelerometers, where you're looking at cables and you want to get their natural frequencies because you can predict the forces in these type of cables. Well, the IBIS system is an alternative to that. Stay cables in particular. There's some rules, but basically this is just talking about the fact that it's a lot faster to do it. Instead of having to mount the accelerometers up on the cable, which is always an access issue, or shining a single laser displacement vibrometer at them to get one cable at a time, you can do multiple cables and a lot faster with the IBIS system. Now you do select the air horn antennas to have a narrower field of view. You can vary those, whether it's a narrow field of view from like 15 degrees up to a displacement transducer. Excuse me, a displacement with a 70-degree field of view, if you had like a dam to look at. So what this show is trying to show you is you look up into the sky, you have to see them. Because remember, if you can't see it, you don't measure it. It's line of sight, speed of light technology. You have to see it. You only monitor that which you can see. So what you've got then is the issue. This is showing the data, and then these are the many cables on this particular bridge. You offset slightly so you can see the cables. You can't hide them behind each other. You've got to see them individually. And they've got to be basically more than about 1.5 meters apart at least, wherever you're shining it into. If they're too close together, you get combined data as well. That's normally not a problem on a bigger bridge. This compares with an accelerometer in the IBIS system. Very similar data results. And the frequencies of the IBIS were actually showing more of the resonant peaks associated with the string theory that goes along with this to show these are better than the accelerometer measured in this particular case. The forces were very similar, very good agreement, so it works well to get the tension forces and check, do you have a cable that is no longer tensioned well, or to get cable tension when you first build it. Well, you have to measure it anyhow. So a summary of this, it's very accurate again. The 0.004 inch, as I mentioned on bridge load tests, you need corner reflectors on concrete bridges. You can get modal vibration measurements up to 0 to 100 hertz, vibration monitoring for stay cable forces from the natural frequencies on many cables at a time. It's quite advantageous that way. One thing I did not emphasize is we did work on the Manhattan Bridge in New York City, which is a great big old suspension bridge with steel cross members underneath every 5.5 meters. We simultaneously saw out to 350 feet, remember line of sight from the Brooklyn side looking out at the bridge, 56 beams and their responses, simultaneously measured. So you got a complete displacement spectrum information and vibrations. So you can see so many more things simultaneously because the radar in a simple sense discretizes the response every 0.75 meters is how it's done. And that's why that works. So you can see a lot of things at once with the technology. It doesn't solve all the world's problems, but it gives you a very nice solution for these longer span medium bridges that can be difficult otherwise. And as I've emphasized several times, line of sight, speed of light technology. So you have to be visible and know where the reflector's at to put it all together. So medium to large stretch bridges up to 500 meters up to 40 hertz in natural in frequency and static out to 1,000 meters. So you can cover quite a long distance too. So we've used it on a number of projects for a variety of purposes. I think it's a useful technology. So with that, I'll open it up to the audience for any questions.
Questions on either of the two topics. I will ask a question since I don't see anybody jumping up. Sure. Cost of this, the device that you showed in the second portion.
Yeah, the IBIS system is not inexpensive. Basically, with training, about $100,000. Yeah. So you won't write the check tomorrow? I don't sell them now. No, but the IDS GeoRadar group has a Denver office, by the way. Nominally $100,000. Years ago, we actually sold this for a while before they opened up an office here. But that was years ago. But they now have their own sales force.
So with the impact echo, could you tell the difference between vertical and horizontal track?
Not with impact echo alone, no. With surface waves, if you are mapping for vertical cracks, you can look at that depth. And so it does work. And that system will probably work at least to 2 feet thick. How much thicker than that it can go, I'm not so sure. But most decks, although Indiana has some decks that are old cast-in-place composites that are 20 inches thick, and it's worked on that, which is an unusually thick deck. It's a beam deck, right?
Yeah.
Okay. Yes, sir?
What would you suggest using for like shorter span bridges?
It'll work fine on a shorter span bridge. Usually the issue is height. Can you get under it and have a 5-to-1 or greater angle? So if it's a taller, shorter span bridge, it'll work fine. But it is a geometry game. You don't want to get flatter than 10-to-1, and ideally 5-to-1. So if it was only 10 foot tall, you have some issues with a really short, small bridge.
So on the impact echo in Indiana,
Yep.
are there plans to go out periodically and rescan the same bridge decks to then try to ascertain degradation and maybe be able to come out with some type of service life modeling down the road? Or is that asking maybe too much?
No, that's okay. We served as a subject matter expert to the SHARP 2 study to educate and support and train 20 DOTs who got some grant money for implementation assistance program. We weren't allowed to be their consultant, but we were helping support them in terms of that. That program is now ending the end of April. But these 20 DOTs, in Indiana is one of them, are definitely looking at their bridge asset management program exactly as you're talking about, to get a database, how much is it deteriorating, that type of thing. So, and because they're all required right now, and some of you, how many of you out of curiosity are certified bridge inspectors? I'm not too surprised in this room. I am. The reason I mention it is if you wanted to do that, it used to be that you'd have to take the 2-week course like you were a technician to become and I could never find 2 weeks. Last year, bless them, they came out with a 1-week course for registered professional engineers who can pass a test and show you know something about bridges. So it's more practical. I finally got to take it. But yes, they're doing it as part of the National Bridge Inspection Standards, and they're integrating. That's the real big step. Almost all of that is visual. So to integrate real data into that program is a step forward, so they can plan it better. Yes?
Impact echo technology, is that applicable to deck with any kind of rebar?
Yes, because unlike some of the ultrasonic pulse echo, which can show you actual rebar locations, although generally I prefer radar, it is long enough wavelengths that unless it's plate steel, you don't see the rebar because the wavelengths go around it. Not a problem. You do have to have coupling. You know, if you had a surface that did not let you excite the concrete, you're in trouble, like a rubber membrane or something. Okay.
All right.
Thank you very much.